Welcome everyone. So in the last lesson, we were actually able to identify some of the chips on the board, including their manufacturer and part number. The next logical step for us will be to look up the data sheets and see what additional information we can gather from there. Before we do that, I think it makes sense to have a really quick chat about embedded systems and how their hardware and software differentiate between the different designs. Now, this is a subject that could have an entire course or maybe even multiple courses on it. So just keep that in mind that I'm going to be doing a really quick and broad overview of these ideas. And of course, there is a lot more information and depth and some caveats to what I'm going to say. So first, if you're not familiar with what an embedded system is or what that means, well, what that's relating to is when we have hardware and software that are specifically designed just to work together, and that software has been designed specifically to work on that hardware, and we're not going to be loading additional software or other features for the user outside of that system in its regular use. So examples of that are our IoT devices, where they just have one specific use, and the hardware and software are designed specifically for that. And that's in contrast to, for example, our personal computers, where we can add additional hardware and peripherals, and we can install, whatever software we would like, as long as the software is designed for the operating system we're running. So I'm going to split these embedded systems up by the type of software that's designed for them, and I'm going to break that up into three different types. And the first one is what is generally referred to as bare metal. So what I mean by bare metal is that, the designers or makers of the software, they're going to write all of the software themselves, everything, and they're not going to rely on any underlying operating system. So everything that their device is going to do has to be handled specifically by their software, and they're going to compile that and then put that directly onto their device and have it run. Of course, this has some advantages in that we then have the most control over our system. However, it also may be the most complex because there are a lot of things underlying that the operating system takes care of us as designers, and a lot of times it's easy to take those for granted. So if you don't want to handle, all of those background processes and everything that an operating system takes care of, but you don't want to move up to a full-fledged operating system like the ones you'll be used to with Linux or Windows, the intermediary option is a real-time operating system, or what is commonly referred to or you'll hear as an RTOS. So these are very common in IoT or lightweight systems. And these operating systems, they still take care of a bunch of the background tasks. So things like scheduling of tasks, interrupts, memory management, and communication between different portions of the system or functions. However, they are designed for much more specific tasks, which makes them, of course, much lighter weight in their size. And it also allows them to run their tasks a lot more predictably, which means we aren't guessing about how long it's going to take to run specific tasks, and running the same task over and over again will give you the same outputs and the same amount of time. This differs from, for example, Windows and Linux, where if you, clicked on some specific task or to open something up, you may have noticed, depending on what's going on in the background, the amount of time that it takes to finish that task can vary. Real-time operating systems are a lot less prone to crashing as well. Another really important feature of real-time operating systems that differs from a standard operating system is that we can set the priority of tasks so that high priority tasks will be completed before low priority tasks, and ensures that they are completed when we need them done. This can be important for critical systems, for example, robotics. Outside of their just timing and predictability, their lightweight size also makes them an excellent choice for IoT devices, so you will see these commonly in IoT devices. Now, I've grouped these two together, the bare metal and the RTOS, because generally speaking, you're going to see these running on a microcontroller. So the difference between a microcontroller and what you may be used to in your home computer, a microprocessor, is that microcontrollers are generally less powerful. However, they will include in them some memory and some ROM, so some read-only memory to store our code. So we can compile our code and store it directly onto that microcontroller, and then it also has the RAM built in that it can access, and we don't need to add those externally to our design. I've added a picture here of an Arduino as an example. So if you're familiar at all with, hobbyist electronics, you may have used an Arduino. So this is an example, not of a consumer one that you would see in IoT devices, but just something you may be familiar with as a hobby designer. The Arduino is a microcontroller design. This is the microcontroller right here. And then we just have all these other peripherals to support, the inputs and outputs to it. So then the third software category that we will chat about is embedded Linux. So in this scenario, the designers will go all the way up to porting a Linux kernel and getting it to run on their embedded system. And then we're running a full-fledged operating system, or close to the full-fledged Linux that you may be used to using. And of course, this offers lots of advantages for us in that the Linux operating system is going to handle all of the things in the background that we are used to it handling. So all of the scheduling, things like networking, it can take care of all of that for us. And then as designers, what we can do is just write bash scripts and binaries and have those take care of whatever functionality we need. So this can be a little bit easier on developers as it's a little bit closer to just developing for standard Linux. So generally for embedded Linux, outside of a few edge cases, we're going to be running it on a microprocessor. And the microprocessor is different from the microcontroller in that it's usually going to be more powerful. However, with it, we are going to require external RAM and an external ROM. So we're going to need extra chips that we're going to have to add onto our board and interface those with our microprocessor, because we're going to need quite a bit more RAM and quite a bit more ROM to run a full-fledged operating system. And we're going to use external specific chips for that. So an example for a hobbyist board, if you're probably familiar with this, the Raspberry Pi, this is running embedded Linux on a single board computer. So embedded Linux is becoming very common in IoT devices just because of its ease to get up and running and write software for. And our router is running embedded Linux, so that we have an idea about the hardware that's involved with it. It will make a little bit more sense, hopefully, when we're looking at the data sheets. So I'm just going to wrap up this lesson here, and in the next one, we will hop over to the browser and try and find the data sheets for these core components of an embedded Linux system that we identified. I'll see you over in the next lesson.